Oh, don't forget, that my office hours, today will be covered by Adam, who's in B of 401. And also, the math club might be of interest to some of you too, because you have people presenting their, their internship, or kind of experiences. But this is kind of a fun assignment. I don't think it's, too taxing. In fact, we talked about some of this stuff a little bit earlier. Suppose you have a computer version with identity. We say the characteristic of R is the smallest positive integer. It's is the smallest positive integer n such that nr equals 0 for all R and R. If no such positive n exists, we say that the characteristic of R is 0. Number A, show that if F is a field, then the characteristic of F is either 0 or a positive prime. Show that if F is a field, then F contains Q or ZP or some positive prime. And this is the interesting one. How many of you have ever messed around with finite fields that aren't just ZP? So it may not even be clear that such a thing exists, right? At this juncture, but this problem tells you what a little bit about what they have to look like if they do exist. Show that if you have a field with finitely many elements, then the characteristic has to be P, some prime, and the order of the field has to be P a power of P, right? So what this tells you is maybe there are finite fields besides ZP and maybe they're not. But Z9 is a possibility. Z125 is a possibility. Z6, or not Z9. I shouldn't say it that way. I'm sorry. A field of order 9 is a possibility. A field of order 125 is a possibility. A field of order 6, not a possibility. Number 2, let R be an integral domain. Let F be a field, and F of X an irreducible polynomial over F. That'll be important actually in later parts of the problem. Show that if R is a PID, then every non-zero prime ideal is maximal. Show that the polynomial ring Fx is a PID. And finally, show that if K is f of x mod this ideal generated by my favorite irreducible polynomial, this is a field containing an isomorphic copy of F. And this field is algebraic in the following sense. Any element of K must be a root of some polynomial with coefficients in F. So none of this business like E being transcendental over the Q, everything actually is a root of polynomial in this case. So this ought to be kind of a fun one. Do next Monday. Okay. Any questions?
Dr. Cardinal, is it Z3 cross Z3? Is that the field of 9 cross? So
That's 0. But
oh yeah.
so let me give you, so we talked about these various kinds of constructions, the compositum of a field, what's a field generated by a set. Let me give you another definition. Lots of kind of definitions. First beginning, definition 14.1.4. Let K inside F be fields and U an element of F. Try again. Oh, death penalty. We say that U is algebraic. U is algebraic over K if U is a root of some non-zero f of x in k. So what it means to be algebraic over the field k is it's just the root of some polynomial, all of whose coefficients, some non-zero polynomial, I should say, all of whose coefficients are in k. If u is not algebraic, we say u is transcendental. If u is not algebraic over k, we say u is transcendental over k. If every element of f is algebraic over k, we say that f is an algebraic extension of k. We say f is algebraic. Okay. And actually, okay, so if you one element algebraic, if every element of f is algebraic, then we say that the extension itself is algebraic. If there exists alpha in f that is not algebraic over k, we say f is transcendental. Okay. So the existence of at least one element that's not algebraic forces us to call the extension transcendental. So here's some examples. F is algebraic over F, right? Any field is algebraic over itself because given A and F, it is the root of the polynomial x minus A. Agreed? So that's kind of silly. Notice that C is transcendental. Over Q.
Well, Dr. Gordon, shouldn't we be saying that these are extensions? Like F is an algebraic extension of F, as opposed to.
When I say the over, that's implicit that I'm talking about an extension.
Okay. It's just like clarifying between like an element and set.
Yeah, so thanks, Neil. That's right. So when it should be implicit in you talking about a set or not, but I mean sometimes they say this is an algebraic extension of. Okay. C is transcendental over Q. By the way, can anybody give a size argument to see why this would have to be true? Let me ask you this. We can all agree, I think, that Q is countable. So would you agree that polynomials over Q also countable, right? Now, imagine, if you will, that every polynomial over Q has a different root, which of course is not true. Take all the linear polynomials, right? Well, all the linear polynomials have roots Q, right? Now, take all the roots of all the quadratic polynomials, right? there's a countable number of these as well, right? Because there's countably many quadratic polynomials over the rationals. So each one of those corresponds to at most two roots, right? Take all the cubic polynomials, right? Look at all three roots of a cubic. It's certainly got three roots in the complex numbers. Maybe it's got multiple roots, but less than or equal to three distinct ones, right? Well, all the cubic polynomials form a countable set, each with three possible roots, so that's countable. Now, take all the quadratics, cubics, quartics, fifth, and what do we get? A countable union of countable sets, which is countable. No way can this be algebraic. It's way too big. There's not enough polynomials to cover everything, right? On the other hand, C is algebraic over R. If I agree with that. Yes.
But why is like if it's transcendental, like if there is at least one root, why is it less?
Here's why it's transcendental. Certainly there are elements in C that are algebraic over R. I is, square root of 2 is, all five roots of x to the fifth plus 2x plus 6 is, etc. But the existence of it, at least one thing that is not algebraic, forces me to call the extension transcendental. And I've got pi and e and various things like that. Okay. Oh, here's another important. If K is a field and X is X is a variable and indeterminate, then Kx is transcendental over K. And in fact, the element X is a transcendental element because the element of X, there is no polynomial that is equal to something in K, right? Other than a constant polynomial in the first place. Okay, here's the first observation. Let K be a field. Whatever this is one six. Let K and F be fields. And U and F transcendental. Okay. And X. Then I always thought this theorem was kind of interesting. There exists an isomorphism P from rational functions into X into KU. And what is more, where phi restricted to where if I restrict this phi down just to elements of K, I get the identity function. I've always found this kind of interesting, right? Because what this theorem really says is, if you take a field and you adjoin a transcendental element to it and look at that field, you can't really tell the difference between that and rational functions. So in other words, if you take Q and adjoin pi to it, And by pi, I mean our old friend from high school geometry. If you take Q and adjoin pi to that, that is an isomorphic field to rational functions over Q in the variable X, all possible quotients of polynomials. And the proof is not too bad. Well, actually, let me call it something different.
Is the K parentheses X, is that always rational functions over K or like over the field?
That is correct.
Okay.
That's rational functions. And this is, remember how we think of this, this is sort of like rational functions with U plugged in, right? As long as the denominator is not zero, and of course, the transcendental case, don't need to worry about that. So there's an obvious homomorphism here, where phi of f of x is f of t, right? Now, obviously, this is going from polynomials, because f of x is actually a polynomial here. We're going to extend this to phi. Let me point out that this is a green homomorphism. So the pitchfork I like to call this the plug-in homomorphism, right? You just take any polynomial and you plug in U, right? And what do you get? You get something in KU, right? This ring that contains all of K and then U, right? Everybody okay with that? The fact that this is a homomorphism is not too difficult because if you look at pitchfork of f of x plus g of x, how do you plug into a sum of polynomials just piece by piece? You get f of u plus g of u. And the same thing with multiplication, phi of f of x times g of x. How do you plug in for a polynomial? A product of polynomials the same way, right? What's interesting about this one is it's one-to-one, right? Actually, it's also it's also clearly onto just by definition of this, right? Because anything in KU, just look at what its polynomial looks like, and that's what it comes from, right? The interesting part is it's one-to-one. One-to-one is the one that depends a little bit on our assumptions. Anybody explain why it's one-to-one?
Since U is transcendental, if you plug it into F, you won't get zero.
That's exactly right. Suppose phi of f of x is equal to zero, but that's f of u, which implies u is a root of f of x in kx. And there's only one polynomial that u can be a root of. F of x must be the identity. It must be identically zero. It's the zero polynomial. Therefore, now because of all this, I can extend this. So we extend to pitchfork, or I'm sorry, phi from kx into ku via The proof that this is a homomorphism is almost the same. You can either use this business right here, or you can use the fact that the way you plug in for rational functions as well is pointwise or multiplied. So and again, from our earlier observations, it's fairly easy to see that this is 1-to-1 now. Because if this goes to 0, that means f of u has to be 0, which is this thing, which means that the original f of x has to be 0. So this is 1-to-1 and onto, because this is a typical element of what round bracket KU looks like. Also notice that P restricted to K is the same thing as pitchfork restricted to K, which is the identity on K. So P restricted to K is pitchfork restricted to K, which is the identity. Because remember, the function is basically plugging into the polynomial for the original pitchfork. Okay. Any questions on that? And notice how this homomorphism identifies X with the transcendental element U. So they're essentially kind of the same thing going on here. Okay, algebraic elements are much more interesting, as you may guess. Theorem. Here, I'm gonna let K be an F and U algebraic over F. Okay. Then number one, K of U. Okay, that's snappy right there. Well, I'll come back to that. Number two, KU is isomorphic to KX mod F. KU is isomorphic to KX mod F, where f of x in KX is minimal, irreducible polynomial for U. Because my hypothesis is U is algebraic, so it's got some minimal polynomial. Well, I'll say something about that too.
Wait, is it equal or iso?
This one, yes, thank you. That one, the first one's an equality, but yes, I should have written an isomorphism for that one. C, the degree of KU over K is equal to the degree of the minimal polynomial. And four, every element in KU could be written uniquely as K0 plus K1U plus K n minus one U n minus one, where Ki is in K and n equals degree of f of x. Again, the minimal polynomial. Number two, you actually, I think, prove on the homework. Well, let me say something about the other ones at least. So let me start off by saying proof. Two is homework. Notice that notice that four follows from three. Well, so let me be a little bit more organized in that. I'm going to take two as a true statement. Let's look at one. Notice that KU that statement always holds, right? Because in a certain sense, let me be sloppy in my exposition here, but KU is basically plugging U into a polynomial coefficient K, and K circle bracket U is plugging into a rational function, right? So anything that I can get from plugging into a polynomial, I could have gotten from plugging into a rational function, and of course, K circle bracket might be bigger, right? This containment always holds. It doesn't matter whether U is transcendental or anything, that always holds. Why does the other thing hold? Right? So why is it true that KU is contained in K? So let me point out that KU is a field and contains, well, and in fact is equal to the quotient field of KU. Right? Because a typical element of KU with the square brackets, typical element of KU with the square brackets looks like f of u, where u is some polynomial, right? A typical element here looks like fu over gu, right? So would everybody agree that this is the quotient of two elements in KU? Right? So that's all we mean here is this is a field that is the quotient field of this. And so we get equality if and only if. So equality holds if and only if KU is a field. Everybody agree with that? So how are we going to get that? Well, consider so this is going to bleed over a little bit into number two. So maybe I'll leave some of it for a fun surprise for you guys, but let's consider this homomorphism. Kx goes to Ku. I call this the plug-in homomorphism, because you take f of x and you just plug in u, right? The kernel of phi is not zero. Why?
Use transcendental. No, sorry, algebraic.
That is correct. There exists some p of x in k of x such that pu is zero. Right? And in fact, we know the kernel is an ideal, right? So zero is a cheat that satisfies that it's in the kernel, but there is some non-zero, I'll make that clear, p of x such that p of u is zero. Agree? So the kernel is not trivial. What is the structure of the ring Kx?
Yeah,
It is PID. So kernel phi this is the set of p of, let's say, t of x such that t of u equals zero. So this is the collection of all polynomials that annihilate u. This is the ideal generated by f of x. And I know that just because of what you said that it's a PID, right? Notice that f of x is the minimal polynomial, right? Because f of x divides every other polynomial that annihilates u. Do I agree with that? So by the first isomorphism theorem, Kx modulo f of x is isomorphic to Ku. Because its homomorphism, by definition, really, is onto. Everybody agree with that? What can you say about f of x?
non-zero.
Let me point out first that Ku is an integral domain. Everybody agree with that? So what does that tell you about f of x? This thing right here is an integral domain. So what does that say about f of x? Anytime's prime time to answer.
It's right.
That is correct, right? Because remember, when you mod out an integral domain by an ideal, or when you mod out a ring by an ideal and get an integral domain, that had to be prime. I agree with that. Now let's see if we can inject some steroids in. F of x is a prime ideal in a principal ideal domain, so it must be, anybody know? Next step. This is actually one thing that you'll prove on your homework, but you might have, depending on how lucky or unlucky you were with order of the point, you may remember it from that. In a principal ideal domain, every non-zero prime ideal is maximal. Does that ring a bell for any of you? Maybe?
So K of here is field.
So K of U is a field, it's magnified, right? So that's basically it. So now we know the kernel has to be has to be prime. In fact, you don't even have to make the observations in the integral domain. You can argue this kernel has to be prime anyway, first principles, because it's, if you have the product of two polynomials that kill you, one of those two has to kill you, so it's a prime ideal. So you can do it from that principle as well. Also notice this integral domain that means prime. Since this is a non-zero prime ideal, the principal ideal domain is maximal. And going back to here, that means that's the field. Right. So in this case, KU and K square bracket U are the same thing. Yes.
Is K square bracket, or, yeah, K square bracket U, is that usually, that's not usually a field?
It's not usually field.
Okay.
In fact, this is what this theorem says. Actually, this is an if and only if, as a matter of fact. That is to say, KU is a field if and only if U is algebraic.
Okay.
Over K.
So by algebra, oh, okay.
So yeah, it's the root of some polynomial coefficients. This one is directly from the homework. So what is the degree of this extension? Now we know that this is the same thing as K square bracket U, and it's actually the degree of this is fine. Why would this be true? Well, I can probably try to do 3 and 4 in tandem. Let's see, KU. I claim let f of x equal a0 plus a1x plus an minus 1 xn minus 1 plus xn be minimum polynomial. Notice that I assume that this polynomial is monic. It doesn't have to be, but I do want the coefficient of xn to be non-zero. And if it's non-zero, I'll just divide out by it. It doesn't make any difference. It's still the minimum polynomial. Are you okay with that? I claim one u squared u n minus 1 is basis for KU over K. Now that I know that that K square bracket is the same thing, and that's really convenient, isn't it, right? Because here, I find this confusing because you have to write everything as a quotient of two polynomials and U, but what a mess. This means that basically you only have to concentrate on the powers of U, essentially. I claim that this is a basis for KU over K. Number one, what does it span? Well, to see that this spans, I think this is going to be the harder part. It suffices to show every power of U can every power of U is in span of the set 1 U squared u to the n minus 1. Anybody know how we're going to show that? show this? There's actually kind of an easier way, I think.
Well, I mean, u to the n is gonna be in the span, because you have the polynomial up there. And then everything else, you'll just have the form for u to the n negative that, because it's a positive over there. Negative that, and then plus u to something else.
He's right. Clearly, every power up to n minus one is in the span, right? Because there they are, right? And his point is u to the n is a linear combination of all the previous. So now we've got u to the n in there. And now you just go by induction. U to the n plus one is do the linear combination of u to the n. You'll get another u to the n out of there if you do it. It's a little flaky, but that's the way it works. Let me give you something that might be a little slicker. So let k of x in kx be any polynomial. Notice I can write k of x is equal to q of x times f of x plus r of x. Does anybody, you smell what the rock's cooking here? Anybody know what I'm doing?
It's the Euclidean domain.
It's Euclidean domain, that's right. With r of x equal to 0, or degree of r of x strictly less than degree of f, which is n. Right? Yes.
How do we have the k of x is a Euclidean domain? Because it's a PID. PID
No. PID is not good enough. It's Euclidean because you can take that as a fact from 4120. But I mean, basically, you show that this algorithm works.
Sure.
That the Euclidean algorithm works.
Okay.
Yeah, and you need this to be over a field, because if you swap this out for an integral domain, it's not a field that doesn't work. But everybody remember that. I mean, you take one poly. In one sense, you can argue that this is why partial fractions works as well, right? You can always reduce this down to you can divide k of x by f of x with quotient, remainder is small, right? How does this help? Well, notice that ku in ku is an arbitrary element. A typical element in ku looks like this, right? And this equation says that k of u is equal to q of u, f of u, plus r of u. Right? Well, what's f of u? Remember, f is the minimal polynomial for u. So in particular, f of u is 0. So this is r of u. So k of u can be written as r of u, which is, say, b0 plus b1u. And some of these coefficients, of course, could be 0, but since the degree of r is less than n, it's up here. So this is in the span of 1 u squared up to un minus 1. So that covers that. So, your proof will work. But I think this one kind of smashes it out quicker by using the fact that, the KX is included. Right, okay with that?
How do we take that fact?
What's that now?
How do we take that fact that it's a Euclidean domain? Like, where does that
4120.
come? Okay.
Yeah, so I mean, you can actually sit down and prove that if you like, but here's what you would prove. If I walk up to you on the street and I give you f of x and k of x, right? And assume that f of x is not zero, then I can divide k of x by f of x, get some quotient and some remainder that's a smaller degree. And you can prove that by induction. In fact, that really what I did is I cheated to get around Schopenhauer's proof, right? Because one of the ways to do that is exactly sort of the idea of that divide. How do you divide? If k of x is a degree bigger than f of x, you just go through one by one and divide through until it doesn't fit anymore, and that's your remainder, right? Okay. Y'all remember that if you have a field K, then K polynomial square bracket X and K double bracket, the power series, right? They're both Euclidean domains, right? And in fact, power series ring is an even easier Euclidean domain. It's almost too bad. So I want to show linear independence. And this one's easier. So suppose R0, R1, Rn minus 1 are Nk, and R0 plus R1u plus R2u squared plus Rn minus 1 un minus 1 is equal to 0. What can we conclude? So u is a root of R0 plus R1x plus R2x squared plus Rn minus 1 xn minus 1 in Kx. Anybody see what has to happen? This thing, in its full degree in glory, was the minimal polynomial for you, minimal non-zero polynomial for you. What's the degree of that polynomial? Less than or equal to n minus 1, right? If I call this G, then degree, if G of X is not identically 0, then degree of G of X is less than or equal to n minus 1, which is strictly less than n, which is the degree of F. And this is a contradiction. Therefore, G of X is identically equals 0. So R0 equals R1 equals Rn minus 1 is 0. So linearly independent. So this kind of covers everything now, because this came up in the proof. The degree of this extension was exactly the degree of F, right? Because my basis has n elements in it, starting my counting at degree 0. So that covers this. F of X was the minimal polynomial. Good. And every element can be written uniquely in this form. Why is this true? Because 1u all the way up to un minus 1 is a basis, and a basis representation is unique. So that establishes the theorem. Okay, any questions? We'll be getting more fun stuff next time. Questions? All right, well, you all have a great weekend. I think about doing math clubs. Other than that, we'll see you on